Hey everybody, welcome to Leetcode Weekly Contest 299. Contest is starting now, so let's go and wish me luck. Hopefully I don't choke. Oh, beautiful, I love getting rate limited. True or false? I can't. Okay, so I mean, this is just some sort of Fibonacci thing, right? Oh, it should be minus 2. I see. Okay, so we have two hard problems. Oh, I've seen this one before. Yeah, I've seen this one, but I don't know where to find it. AC. Okay, almost 1000. I mean, I just need some sort of smart brute force. Okay. I'm just working out some details on paper. Okay. Okay, so let's just do a DFS. Okay, now Okay. Can DFS from I. Okay, so now I need to debug. Oh. Nine zero. I see. Okay, so no bugs at least. I don't know how fast that was. 14:12. It's an all right time, but because question 4 has come up before, I'm sure some people have copy pasted from somewhere, but I don't actually know. I don't know where to find. I've seen it in Discord before, but I think it would be kind of cheap to go and copy paste that, so I worked it out by myself. Anyway, I guess I'll go through the solutions now. Okay, question 1 is, it's pretty straightforward. You just do exactly what it says. So I'm iterating through every cell. Is diag checks, it will be true if the current cell is on one of the diagonals. It will be on this top left bottom right diagonal if the I component and the j components are equal, and it will be on the anti-diagonal if they sum to n take 1. And if this diagonal condition is not the same as whether it's non-zero, then it will return false. So there's not much to it, just O(n) squared. Okay, in this problem, this is like a Fibonacci problem, I think. Yeah, it's a Fibonacci problem. Basically, each side of the street is like completely independent. So if we just solve the answer for one side of the street, then we can simply square that and yeah, just return that because they are independent. So we're going to solve only for one side of the street. And now the number of ways to put ways to choose n things, each of them being 0 and 1, such as there's no two adjacent ones, which is basically what we want. That's the Fibonacci sequence. But I wasn't sure it was the Fibonacci sequence, so I have this is basically like a DP. Like dpx is the number of ways for x plots, and then when we're finding the answer for x plots, either we don't put a house on the xth plot, in which case I take 1 is the number of ways to do the remaining plots, or we do put a plot on the current plot. In that case, we can't put a house on the I take 1th plot, so we'll solve for I take 2. This is just the base cases. Yeah, so the reason why I use n plus 5 here and like -1 is because when I equals 1 here, I'm using negative indices in Python, which wraps around, but it's not very clean. You don't need to use an array. You can just calculate Fibonacci, and actually, yeah, that would lead to like O1 space complexity if you really want, but I don't really care about that. Okay, in this problem, okay, so the score is the maximum of sum of nums1 and sum of nums2. Basically, we can just find what's the maximum possible sum of nums1. Yeah, we'll find the maximum possible sum of nums1, then we'll switch around nums1 and nums2, resolve the problem, and then take the max of both options. So that way we don't need to worry about the max condition, we can just focus solely on sum of nums1. Now, if we think of sum of nums1, what will be its, so we have nums1 and we have like nums2, and let's say I choose the subarray x to y, then what will be the sum, the new sum of nums1? Well, it will be the old sum of nums1, and then it will be nums2 I take nums1 I for I in this range. Basically, what this is saying is for each element which is changed, I increment, I increase the current sum by the difference between the two positions. Because, for example, if like nums3 equals 6, nums2 3 equals 8, and I chose this subarray 2 to 4, then when I get to the third element, which is changed, I need to increase the current sum by 8 subtract 6. Okay, so we just need to maximize this. Now, sum of nums1, that's the old sum, so this will be a constant. So all we need to do now is, what is the maximum possible of this for some subarray? So if we define a subarray such that ai equals to nums2i take nums1i, then the new question is, what is the maximum sum of any subarray in A? Which, since this is just the max subarray problem, you can just use Kadane's algorithm, which is the dynamic programming one. I think it's fairly standard, so I won't go over it. Not really. Yeah, but basically, G of AB just solves it. It will return the old sum plus the Kadane's algorithm on this change array, and then I'll output the max of both options. Let's just have a glance at my rank. So it looks like I'm rank 4, which is pretty good. What I really want is rank 2, because I haven't gotten the gaming mouse before, but I guess I'm getting another backpack. Anyway, let's look at this problem. So in this problem, since n is small, there's only like n take 1 edges, so there's only going to be on squared pairs of edges, which means it suffices just to brute force over every pair of edges, and then all we need to do is we need to come up with a smart way of determining the XOR quickly. So we can't afford to calculate the answer for each pair in on time, because that would lead to an on cubed overall time complexity, and that's too slow. So instead, we do some pre-calculations and stuff. Okay, basically, I find it easiest if we root. Often in tree problems, you want to root the tree so we can do dynamic programming over subtrees or something. So in this case, I've just rooted the tree at node 0. I'll probably just be referring to this diagram, even though it has node 1 as the root, but it doesn't really matter. Basically, that also means that instead of iterating over edges, we can basically iterate over nodes, because we can refer to an edge solely by the node which is lower down in the tree. So for this red edge, I'm not sure if my mouse is on screen, but for this red edge, we will refer to it purely by the node 0, since that uniquely determines the edge. Basically, there are two cases. The first case is when the two edges, like one of them is on top of each other. So for example, if we have this 1, 3 edge and this 3, 4 edge, that's one case. No, the two edges don't have to be next to each other. Basically, the case is when, if we refer to the edges by their nodes, it happens when one of the nodes is in the subtree of one of the other nodes. Yeah, so for example, if I was to root this tree at node 2, then this edge between 1 and 2 and this edge between 3 and 4, that would lie in this case, since node 4 would lie in the subtree of node 1. And the other case is, for example, these two highlighted red nodes. That's when these nodes are not in each other's subtrees. And the reason why I'm splitting them into cases is, it's basically, there's different methods to get the XOR for each case. So let's look at the first case. The first case is when one edge is like, one of the nodes is in the subtree of the other nodes. That is, one edge is like somewhere an ancestor of that edge, kind of. And basically, if we have these two things, that breaks the tree into, one subtree will be from the lower node down, the subtree of the lowermost node. And remember, I'm talking about the nodes which correspond to the two chosen edges. One of the subtrees will be the subtree formed by the lowest node. One of the subtrees will be like all the nodes in between like the two nodes. And then the third subtree will just be everything else. And in this case, if we pre-calculate for each node, what is the XOR of all nodes in its subtree? That means that we can actually get the XOR of all three components quickly, because one of the components will just be a subtree, so we can look that up. One of the XOR components will be it will be exactly the nodes which are in one subtree, the nodes which are in the subtree of the higher up node, but are not in the subtree of the lowermost node. Which means in that case, the XOR is actually just the XOR of the two pre-calculated values. That's because like XOR sort of cancels out itself. So by taking the XOR of the higher node subtree and then XORing that with the subtree value of the lowermost node, that will give us the second component. And then finally, if we have two of the components, we can work out the third XOR as the XOR of all nodes, XOR the nodes which are in the first or the second component. That's one case. The other case is when the nodes are not in each other's subtree. In this case, it's pretty easy because two of the components will just be the subtrees, two of the components is just the subtrees, and the third one is just the remaining nodes. So all we need to do now is calculate the XOR of all nodes. The way I've done it here is first I will do a DFS, and in this DFS we will let precal x be the XOR of all nodes in the subtree of x. And I think this should be fairly straightforward. Child x is just so I can direct the edges, so it allows me to DFS over a rooted tree more easily. Then the way I've chosen to do it is because it's kind of hard to tell if two nodes, one of them's in the subtree of the other or not. You can do it. with like a Euler traversal, pre-order traversal, or something like that. But the easier way I found is we will just iterate over the highermost node, and then we'll just do a DFS in the subtree of that highermost node, and then we'll iterate over all nodes that we just processed as the lowermost node. So that's what I'm doing here. For each of the highermost nodes, I'll perform the DFS, and then I'll just iterate over all of the lowermost nodes. I'm excluding comp 0 because otherwise I and j would be equal, and they can't be equal. Then I will mark process ij and process ji being true. And that means that when I loop over all remaining pairs, if I haven't processed them yet, that means that they're in the second case where they're not in the same subtrees, and then I can do the second version. So overall, the first DFS takes on time. I'm performing this on DFS n times, so that's n squared. I'm looping over n squared pairs in total as well. So overall the complexity is n squared, which is good. Okay, let's just check if my ranking changed. It looks like it didn't. So I got rank 4, and that's pretty good. Anyway, thanks for watching, and I'll see you guys next time.